So this is video 2.3, Introduction to Orbitals and Wavefunctions. So we're moving from the classical orbit idea with electrons orbiting around the nucleus, just like planets orbit around the sun kind of thing, to an idea of an orbital, which is based on our quantum knowledge. So the first thing to and here's like an idea of an orbital. So instead of having the electrons orbiting in circles, you have these areas where it's likely that the electron will be, and there's other places that are nodes that electrons can't be. So to get a better idea of what's happening here, we need to have a look at something called the wave function. The wave function is something that you don't need to calculate. Comes from an equation called the Schrödinger equation, which is an incredibly difficult to solve second order differential equation. But the wave function is basically a value that highlights the probability of an electron being there. In fact, if you take the complex conjugate of the wave value and square it, that is the probability of finding the electron in that area. And there's a pretty simple diagram. You can see we've got the wave function and some idea of the wave function squared kind of thing, and the distance from the nucleus. You can see that at the nucleus there's no probability of an electron being there. So that's giving you an idea that there's no chance that an electron's going to be in the nucleus. But you can also see that the probability is highest at sort of an intermediate distance away, and it tails off again, so you can get electrons sort of further out, but most of the time they like staying sort of a good distance away from the nucleus. So the idea of a wave function sort of gives you an idea, first of all, that the movement of electrons is probabilistic, and it's related to the idea of uncertainty in quantum theory. So you can't know where something's going and its speed at the same time. So that's Heisenberg's uncertainty theorem. You don't need to know all the specifics and all the math, but you do need to have a qualitative idea of the fact that the motion and where electrons are around an atom is a probabilistic thing. So if you have a nucleus here, you're going to have most of your electron, if you took a time-lapse photograph of where the electrons were, they would be gathered like this, and maybe some out here, a bit more sparse. And that's for a really simple model, for say a hydrogen atom, where you have one electron in the system. When we introduce more electrons, the probability distribution is not entirely symmetrical. In fact, you get these nodes and lobes and stuff forming. The math behind it is very complex, but we'll have a look at some of the nodes that form. So these are what we call orbitals. The simplest one is the 1s orbital, which is the first one. It fills up with 2 electrons. It's circular, so you get 2 electrons. If the only node is the nucleus, so you get 2 electrons that primarily distributed in here, sometimes out here. This is a line that shows sort of the greater probability exists within here. Something like 95% of the time the electrons are in here, but sometimes they are out here, very occasionally. So you can already see that in hydrogen and helium, they only have a 1s orbital. Hydrogen has 1 electron in the 1s, and helium has 2 electrons in the 1s. It takes 2 electrons. So the 2s electron is a very similar thing. It has 2 nodes. It has a circular node inside. So electrons can be in here, they can be in here, but they can't be on this line, and they can't be in the nucleus, but they can be out here as well. So it has a circular node. That's the only difference from the 1s. It's a bit bigger as well, but it also takes two electrons. Now we get a little bit crazy because we're looking at 2p orbitals. So the idea of a circular orbital makes sense. You're orbiting something. It's a bit probabilistic. The electrons are a bit random, but it sort of makes sense. the 2p orbitals make absolutely no sense, but they do exist. There's a lot of experimental evidence that the electrons do behave this way, and it contributes to bonding and to how the atoms interact. So the 2p orbitals all are very similar in that they have a node at the nucleus, but they also have a planar node, so no electrons exist along this line, which is essentially the x-axis, or the y-axis, or the z-axis. So that's why you get three separate 2p orbitals: 2px, 2py, and 2pz. Each of these can take 2 electrons, so in the 2p system you're taking a total of 6. 2 in here, 2 in here, and 2 in here. And it's not 1 in each lobe, they're probabilistic between either lobe. So that is the idea of, and these are also, I should mention, 3D structures. So this looks like that kind of thing. The 1s and 2s orbitals are also 3D structures, they're spherical. So the 2p has these planar nodes and can take 6 electrons, and there's an x, y, and z version. Now, something to note, if you look at the 2s and the 2p together, you get 2 electrons plus 2 in each of these makes 6. 2 plus 6 is 8. So that's kind of where your octet rule comes from. People noticed, oh, they seem to want 8 electrons. That's because they're trying to fill up the 2s and 2p before they become a stable noble gas type arrangement. So what bonding is about, what classical bonding theory was really about, was actually just filling up 2s and 2p orbitals, or your 1s orbital in the case of small atoms. Now, going on, 2p brings you up to argon, so you've got hydrogen, helium, lithium, beryllium adding into 2s, boron, carbon, nitrogen, oxygen, fluorine, neon's the next noble gas. Neon fills up all of the 2p orbitals, so once they're all full, you need to move on to the 3s orbital. The 3s orbital is again a circular orbital with, you guessed it, 3 nodes. So for the s orbitals, the number at the front, which is the principal quantum number, which n, that signifies the number of nodes, but we'll get to that a bit later. You can also have 3p orbitals, which have some extra nodes, but then one last class of orbitals I want to mention is the d orbitals. You actually have 5 different types of d orbitals. 4 of them look like stars, like two perpendicular p orbitals, almost, and they are the 3dx squared minus y squared, 3dx squared y squared, 3dxy, 3dxz, 3dyz, and then the 3dz squared. So 4 of these look very similar to each other, and sort of a progression. You go from circular to 2 lobes to 4 lobes, kind of makes a bit of sense. But you actually have this 3dz squared orbital that has 2 lobes like a p orbital, but it also has a ring lobey thing, like a donut circled around the outside. So if we want to just have a look at this, because it's an interesting structure, if nothing else. So there's your nucleus, there's your lobes, and you also have this donut structure around the outside. So that's what and that's also a lobe, and you can get, electrons are highly probable to be in that lobe as well, that donut shaped lobe. So there's definitely some interesting stuff going on with the orbitals, but it's just having an idea, going back to our wave function, that the highest probability is that they're inside of these orbitals, but not in the nucleus, so, and not along any of the nodes. So the only things you need to remember: what a wave function sort of means, what it means from a probabilistic point of view of where the electrons are going to be, and then the shapes of each of the orbitals. S being circular, P being sort of 2 lobes, and D being 4 lobes, and this one exception with the 3dz squared being 2 lobes and the donut shaped lobe. And you might be expected to draw these, especially up to 2p, because they're not incredibly hard, but and label them as well. They go in the X, Y, Z axis, so that's all pretty easy. But I think it's really cool to just see how quantum theory and the idea of the wave function and what you derive from the wave function being these orbital nodes and stuff and orbital lobes, how that fits in with what people discovered before quantum theory, which is the Octet Rule, 2 electrons going to each, and later on we'll see it fits in with a whole bunch of other things, electromagnetism and stuff. So we'll see that next time.